everyone, I'm Mengjiang Lin, and I'm a second-year DPhil student from University of Oxford in the Peterborough group. So today I want to give a quick research talk about my current research project, that is to use the Benchtop nuclear magnetic resonance spectroscopy to optimize battery electrolytes. So, first of all, what is a benchtop NMR spectroscopy? You might not be familiar with NMR, but it's an extremely powerful technique in which a particular isotope of an element in our sample is probed by a radio frequency pulse under an external magnetic field. So this provides us information about the chemical structure, environment, and concentration of the probe nuclei. Basically, benchtop NMR is just a smaller version of it. So benchtop NMR use a permanent magnet that can help us to remove the accessibility barrier of the large NMR systems. But in the past, the benchtop NMR are limited to just a few nuclei and often had blind spots for some compounds. Oxford Instrument X-Pulse is the only true broadband spectrometer in the world that can help us not only collect spectra from proton and fluorine, but also can excite and detect a wide range of other nuclides such as carbon-13, lithium-7, phosphorus-31, etc. So, in addition, it is also capable to perform two-dimensional spectral method, along with relaxometry and the pulse field gradient. This is sometimes also called diffusion NMR. Battery technology is often considered as a balancing act between 5 key parameters. That is the energy density, how much charge can be stored in our cell, the power density, how quickly the charge can be extracted from the cell, safety, how safe the cell is, and lifespan, how quickly the charge density is reduced over time, and of course cost, how much energy costs per unit currency. So here is an example of the current battery chemistries defined by cathode materials and how do they balance these 5 factors. But as we can see in my later talk, benchtop NMR can help us to optimize all of these 5 factors effectively. So, usually speaking, in a non-aqueous electrolyte dissolved in an organic solvent or a mixture of organic solvents, the majority of the compound will be visible in a simple proton spectra. So here's an example of a commercial electrolyte, and as we can see, all the peaks here are very distinctive of each other. And for example, the red peak here represents diethylene carbonate, and the blue peak here is attributed to dimethyl carbonate, and the yellow peak here is characteristic of ethylene carbonate. And so from the proton spectra that can be performed within 2 minutes, we can conclude the major components of our electrolyte. And in addition, due to the broadband feature of benchtop NMR, we will be able to get multi-nuclear NMR spectra at the same time. So this provides us even more information about the chemical composition of our electrolyte. So for example, here is a multi-nuclear NMR spectra of a commercial electrolyte. As we can see here in the phosphorus-31 spectra, the signal is split into 7 peaks, which means that it's coupling to 6 identical nuclei, and at the same time, as we can see from the fluorine-19 spectrum, it's split into a doublet, and we can tell from the spectra that the distance between the doublet and the septet are the same, and so we can safely say that the 2 nuclei are coupling to each other, and this is characteristic for hexafluorophosphate, which is a very commonly used anion in electrolyte. And also, in addition, the broadband feature can help us to detect the degradation products in the electrolyte. over time. So, for example, here shows the two NMR spectra of two electrolytes that give different performance under cycling. And you may say that we cannot tell any difference from the proton NMR spectra. However, if we take a closer look to the fluorine spectra, we can observe an additional doublet here. So actually, this according to the chemical shift, we can attribute this additional doublet to difluorophosphoric acid. And this compound is characteristic of a hydrolysis reaction between hexafluorophosphate and the unwanted water in the electrolyte. So with the help of different nuclei spectra, we can easily detect the unknown species in our electrolyte. So this can help us to understand the degradation product and the degradation mechanism as a result. So usually speaking, the electrolyte degradation mechanism is quite complicated and often involves several steps. Therefore, our goal is to move as much as our analytical activities into operando studies so that we can achieve temporal information along with structural elucidation of our electrolyte degradation. So, in addition, the size of the Benchtop NMR allows it to be contained in an inert atmosphere because, as you may know, usually most of the battery material are extremely air sensitive. This could reduce contamination from sample handling in the air. And as a summary, Benchtop NMR can help us to improve all the 5 key parameters I mentioned before. So because we can measure the peak area under our peak, this is representative of the ionic concentration of our cations in the electrolyte. So we can infer the energy density of our cell. And due to the diffusion NMR measurement, we will be able to measure the ionic mobility in the electrolyte. This helps us to measure the power density of our cell. In addition, since we will be able to elucidate the new degradation product in our electrolyte, we will be able to understand the electrolyte degradation mechanism so that we can improve the lifespan of our cell. And the ability to perform an NMR analysis like in a lab next to where you are developing your new electrolyte formulation is also a huge help for you to reduce the cost of analysis and reduce the cost of like the poor quality electrolyte. So NMR is a very powerful technique in battery research, and hopefully this technique can be applied to help us promote the sustainability of our planet. And finally, I would like to thank the Peterborough Group for their help and support during my research, and Oxford Instrument for funding my project, and of course, Royce for funding this equipment. Thank you very much.